All right. Welcome everyone viewing this video later. I doubt anyone's going to join while I'm here, live while I'm here, though you're certainly welcome to do so, since we all have fall break now and we're all on vacation. But I wanted to be sure to get this review session up as soon as possible before the next exam, which is this coming Friday. It's a week from yesterday. So I wanted to go over the practice problems, I would say all of which are relevant and are problems like unto those that will be fair game on exam number 2. So exam 2, as the syllabus says, is on chapters 19, 20, and 28. So all of these questions, I would say, are relevant to that. So if you look at the accompanying supplemental section that comes with the practice questions, you see I give you a bunch of structures, and I'm going to do the same thing on your exam number 2. I was very clear, even though I was out of town, that you do not have to memorize the 5 nitrogen bases, and you do not have to memorize the structure of ribose. So you'll get something like this. I'm probably also going to import this text over here into your supplemental section. This tells you how to know what abbreviations you can use on exams without losing points. And so I would suggest you read that ahead of time, or at least read that when you get the exam, because this, I think, makes that whole idea pretty clear. Good, on to the actual exam practice questions. The first question is what I would call an active style mechanism, in which you're given all of the structures and you just have to supply the curved arrows. And this is a reaction we never talked about in class. And these types of reactions, these types of questions, I should say, still give you enough information that you can figure out the answer. And the way you do it is you compare each structure to the one that comes next, and you consider what changes have taken place. And by that, you can know which curved arrows to add. And if you compare what we're starting with here, we're starting with aniline and the NO plus ion. And also what we're ending with basically is formed the new nitrogen-nitrogen bond. You can see the NH2 of the aniline has become NH2 plus, and we've lost the triple bond between nitrogen and oxygen, and now have a neutral oxygen atom. Looking at it, I kind of wish I had drawn the lone pairs on oxygen. But either way, even without them, you can tell that the oxygen is neutral, that the plus charge has gone away. So the only way you can really accomplish that is by the NH2 nitrogen attacking the nitrogen in the nitrosyl cation, NO2 plus, breaking the nitrogen-oxygen pi bond, and putting the electrons on oxygen. So those are the arrows you need to add for the first step. In the second step, we can tell that we've gone from NH2 plus to NH. That nitrogen now has its lone pair back. And so the only way we can do that is by pulling off one of these 2 protons that are on that nitrogen. And we happen to have a water molecule conveniently right here. Active does the same thing to pull off that proton for us. So we start our arrow at either of the 2 water lone pairs on oxygen. We point the arrow at the hydrogen, and then we break the nitrogen-hydrogen bond and push the electrons onto nitrogen, something like that. And that gives us this structure. When we compare this structure to the next one, we can see the only change is that the oxygen has gone from neutral to a plus charge, and there's a new oxygen-hydrogen bond that wasn't there before. In other words, we've protonated the oxygen atom, and here we have a hydronium ion ready to do that for us. So we just start the arrow at one of the oxygen lone pairs and end it at the hydrogen. And then we break the oxygen-hydrogen bond and push the electrons onto oxygen. Just a standard protonation using a hydronium ion. And that gets us to this structure. If we compare this structure to the next structure, we can see that we've gone from a nitrogen-oxygen double bond to a nitrogen-oxygen single bond. We've gone from a nitrogen-nitrogen single bond to a nitrogen-nitrogen double bond, and we've lost the proton that's attached to the nitrogen. And we're given conveniently here a water molecule to accept that proton. So in order to go from a nitrogen-oxygen double bond to a nitrogen-oxygen single bond, we need to break that pi bond and push the electrons onto oxygen. That will get rid of the plus charge on oxygen. In order to make the nitrogen-nitrogen double bond, we need to use the electrons in the nitrogen-hydrogen bond in order to form that double bond. The way we know that we don't use the lone pair on nitrogen is because the top structure has a lone pair on nitrogen and the bottom structure does also. That tells us not to use those electrons. Instead, we need to use the electrons in the nitrogen-hydrogen bond to form that nitrogen-nitrogen pi bond. And then, of course, we need something to accept that proton, that H+ ion. And we just happen to have a water molecule over here that can do that for us. So we use the water molecule to pull the proton off nitrogen. The electrons in the nitrogen-hydrogen bond go in between the two nitrogens, forming a double bond, and the nitrogen-oxygen double bond breaks and the electrons go onto oxygen, getting rid of the plus charge on oxygen. And so that gets us to this structure. Then if we compare this structure to the next one, we can see that we've protonated the oxygen. And that's straightforward to show. We start our arrow at the oxygen and end it at the hydrogen on the hydronium ion. And then as usual, we break the hydrogen-oxygen sigma bond and push the electrons onto the positively charged oxygen. That gives us a water molecule and the protonated species here. And then, in order to get from this structure to this structure, we need to lose this molecule of water and form another nitrogen-nitrogen pi bond. We go from a nitrogen-nitrogen double bond to a nitrogen-nitrogen triple bond. And you can tell we've gone from a neutral nitrogen atom to a nitrogen atom with a plus charge. So the way we do that is we push the electrons from nitrogen in between the two nitrogen atoms. We break the nitrogen-oxygen bond and push the electrons onto oxygen, losing a water molecule. That gives us this species, which is known as a diazonium ion. That was actually mentioned briefly in chapter 16, though we never talked about it. We didn't go over it. But these are very powerful electrophiles. And you can use these species in a couple of different ways. With one of them, you're doing essentially a nucleophilic aromatic substitution, or you can use them as an electrophile in an electrophilic aromatic substitution. And that's what we're doing here. We've got here a molecule of anisole, which is methoxybenzene, and the anisole ring, the benzene ring, forms a new carbon-nitrogen bond right there. And so in order to do that, we're doing essentially a standard electrophilic aromatic substitution. The electrons in the benzene ring and the anisole will attack the nitrogen atom. Now, how do you know which nitrogen to attack? The way you know that is we can't attack the nitrogen with the plus charge directly, even though it's tempting. The reason we can't do that is because if we can't form another bond to that nitrogen. It already has 4 bonds. Nitrogen can never, ever have 5 bonds around it. Phosphorus can, nitrogen can't. So in order to get rid of the plus charge, we have no choice but to break the nitrogen-nitrogen pi bond and push the electrons onto the nitrogen with a plus charge. And in order to do that, we need to have the benzene ring attack that terminal nitrogen atom. So we're going to break the carbon-carbon pi bond and push the electrons onto nitrogen like this. So we're going to form a bond. What that arrow means is that we're forming a bond between this carbon and the nitrogen atom. And so that's this new bond that we formed over here. Just like any other electrophilic aromatic substitution reaction. This is just like electrophilic aromatic halogenation, electrophilic aromatic nitration, both Friedel-Crafts reactions, electrophilic aromatic sulfonation. I think I'm forgetting one or two of them, but you get the idea. So we get now this intermediate. This is a resonance stabilized carbocation, but we want to restore aromaticity to the ring. And in so doing, we need to remove that proton, just like we've always done in an electrophilic aromatic substitution reaction. Unlike in the electrophilic aromatic substitution reactions we went over, we've actually got water around. So that's a perfectly reasonable base to accept that proton and form a hydronium ion. And then we shift the electrons in the carbon-hydrogen bond back into the aromatic ring and restore aromaticity. And this type of species is known as an azodie, like it says in the problem. They're generally very brightly colored. And there's some famous undergraduate lab experiments where you make these things and actually test using fabric test strips how well different types of fabric take the dye. So you might actually get to do that in lab. It's kind of fun. It's a mess. You get dye all over your hands. Well, wear gloves. Certainly don't wear your best clothes to that lab. They're kind of messy, but they're fun. Good. So that's how you approach a problem like that if you're given a problem like that. That type of question is certainly fair game on any exam, and you run into them in active also. That brings us to the next page where we have some questions about chapter 28 on nucleic acids. So I've summarized, where did I put it? I've summarized at least most of the material that you'll be responsible for in chapter 28 over here. I don't promise this is absolutely everything, but it should be at least most of it. And if you watched the video that I posted on chapter 28, you'll learn that the nucleic acids, DNA and RNA, use 5 different nitrogen heterocycles in order to form the famous base pairs that are in the helix. The double helix of DNA and RNA is a slightly different structure, but there are hydrogen bonds that bond the two strands together. And so you can see with all these nitrogens in them, there's lots of opportunities for hydrogen bonding. So there's 2 types of nitrogen bases in nucleic acids, the purines, which are here in the top, these 2 structures, guanine and adenine, and the pyrimidines, which are these structures on the bottom. Both purines are found in both DNA and RNA. As for the pyrimidines, thymine is found in DNA only, uracil is found in RNA only. And the difference between these 2 structures is just this one methyl group over there. Thymine has that methyl group where uracil has a hydrogen. And then the last pyrimidine, cytosine, is found in both DNA and RNA. And everything I'm saying here is included in what you will have to know. I don't promise I'm saying absolutely every single thing you'll need to know here, but I'm trying to cover at least most of it as it comes to my mind. And so, and again, you'll be given the structures of the 5 nitrogen bases and of ribose. I do not expect you to memorize those. So the first questions are asking us about which of the nitrogen bases are found in DNA, which are found in RNA, and which are found in both. And you just follow the directions here. So a purine base found only in RNA, well, we've already said both purines are found in both DNA and RNA, So there is no purine base that's found only in RNA. So the correct answer here would be N, for none of the above. I don't promise your exam questions will be phrased exactly like this. So you need to understand this material. And then we have a purine base found in both DNA and RNA. Well, either of these is correct. You'll put, the question specifically says to put only one, but in this exam, whichever year I gave this, I would have accepted either guanine or adenine, since both are equally correct. Neither one of those is safer or more correct than the other. They're equally correct. And then we have a pyrimidine base found only in RNA. Like we said, that would be uracil. If it had instead said a pyrimidine base found only in DNA, we would put thymine. But uracil is the one that's found only in RNA. And then we have a pyrimidine base found in both DNA and RNA. That would be cytosine. Cytosine is found in both DNA and RNA. So like I said, I do not promise if there's questions like this that it will look exactly like this. In fact, I can pretty much promise you if I ask you something like this on the exam, I will change the phrasing a little bit to make sure that you really understand. But these concepts are certainly fair game. And a question like that is certainly fair game. Good, so let me just make sure I haven't missed anything. Nope, that looks good. And then in the next question, we're asked to draw a dinucleotide. And you would certainly be responsible for a question like that too. It says, draw a GC dinucleotide of the type found in RNA. So we need to understand what that means. And since it says it's of the type found in RNA, we're going to use regular ribose, which looks like this in the sugar phosphate backbone. If it were instead a DNA type nucleotide, you would use 2-deoxyribose, which looks like this. And the difference is ribose has an OH on carbon number 2, and 2-deoxyribose is lacking that OH group. It just has a hydrogen there. So this is the sugar used in DNA. This is the sugar used in RNA. You will be given the structure of ribose, but I expect you to know what to do with it. Good. Well, I actually am able, since we're looking at RNA, I can save quite a bit of time here. The first nucleotide is a guanine ribonucleotide. So here we go. There is our ribose ring down here. Notice the CH2 right over there. You can either use a line angle drawing or write out CH2. I expect by now you're in your 4th semester of chemistry. I expect by now that you don't have to ask about every little thing like that you understand that there's multiple correct ways to draw any structure, any of which will be accepted. So whether you write CH2 or just use a line angle drawing, either one is equally fine. So this is how we connect up the ribose. Remember from the video that the nitrogen base, since it's purine, connects at nitrogen 9 over here. So we go from an NH bond to a CN bond. And this type of functional group is called an NO acetal. And we learned what an acetal is in chapter 19. That's also part of the exam material, in which case you have a C bonded to 2 OR groups. So instead of a regular acetal, you have an NO acetal. The carbon is bonded to an oxygen with an alkyl group attached and a nitrogen with alkyl group attached. So it's a similar type of structure. We've just replaced an oxygen with a nitrogen. So that's the first one. Also part of what you will need to know is that the sugar phosphate backbone continues through carbon 3 of the ribose. That's this one over here. We call that the 3' carbon. So you need to know that. You also need to know the structure of a phosphate group. I'm just going to put OH for now, but that's destined to become an oxygen-carbon bond. That oxygen on the phosphate group is now connected to the CH2 of the next ribonucleotide. The next one is cytosine. So I'm going to put CH3 for now. Once I form the bond, that's destined to become a CH2. Kind of running out of room over here. So here's what I'll do. There we go. So we've connected the phosphate ester to the 5' carbon of the next ribose. I've here put the numbering on the ribose and deoxyribose rings, but the connection is from the 3' carbon of one ribose to the 5' carbon of the next. So here's the 5' carbon of that ribose. And here's the 3' carbon of that ribose. Notice there's always a single phosphate in between those two. That's something I'm sure I pointed out in the video. So we've got most of our dinucleotide ready. The only other thing it says is put a diphosphate group on the free 5' end. So the other 5' end is over here. That was originally OH, but we need to switch that to another phosphate group because we only have a monophosphate, so we need to make it a diphosphate. Again, I expect you to know what the structure of a phosphate group is. There we go. I also should point out these wedged bonds are optional. You don't have to wedge the bonds in. You can, but if you just want to draw straight lines like this, it's perfectly acceptable. So I think that's it. We've got a guanine nucleotide. We've got a cytosine nucleotide. The two of them are connected by a phosphate ester going from the 3' end of the first one to the 5' end of the other. And then it says put a diphosphate group on the free 5' end. This would have been OH originally, but it's instead O-diphosphate. Let me check my answer key and just make sure I've not made any mistakes. Nope, everything looks good. Now, the other thing is, if one of these nitrogen bases were uracil, then you would need to know that you're drawing an RNA-type nucleotide, even if it didn't specifically say to. And similarly, if one of the nitrogen bases you're given is thymine, then even if it doesn't say to draw a DNA-type nucleotide, you need to know that thymine is found only in DNA. This is something covered in high school biology, so I don't think that's asking very much. But yes, I admit I'm able, I have the advantage of speed. I can draw these things pretty quickly, but that is how you'd put together the dinucleotide. And that's pretty much it. All right, I think we're done with this document. We're done with this document. And that gets us back to here. Here we have some synthesis problems. And I notice this first one is particularly interesting. Because there's actually multiple correct answers. Let me just move this one down. So this one is asking to convert this alkyl chloride into a carboxylic acid. When you get a synthesis question or any type of question like this, always count carbons. That will let you know what you need to do and what kind of change you need to undergo. Besides the phenyl group, the starting material has 3 carbons. Besides the phenyl group, the product has 4 carbons. So we've added a carbon. And we've learned a couple ways of doing this. The one that's in your answer key is essentially exactly what you did in lab. You could treat this first with magnesium in either diethyl ether or THF. Both are equally acceptable. And then with carbon dioxide, and then with dilute aqueous acid. That's carbonation of a Grignard reagent. So you go from Cl to MgCl, you make the Grignard reagent, then you add CO2 and you make CO2 minus, then you protonate it and make CO2H. That would be fine, but there's actually another correct answer. That's the one in the answer key, but there's another correct answer. You could also treat this chloride with sodium cyanide in maybe a polar aprotic solvent like DMSO, and then hydrolyze the nitrile that you get. So you start with the Cl over here, treating it with sodium cyanide does an SN2 reaction, and you go from Cl to Cn. So you get the nitrile, just like we talked about in class yesterday. And then when you hydrolyze the nitrile, you get the carboxylic acid. So that's fine. At the time I made the answer key, whenever that was a few years ago, I didn't foresee that answer, but I guarantee you, some people put that answer and I accepted it. It's perfectly correct. That would also result in the carboxylic acid. So either of those answers is correct. The next one looks like it requires a Wittig reaction. And in order to have a Wittig reaction, we need to have a ketone or aldehyde. And you can tell where the ketone or aldehyde needs to go, but based on where the carbon-carbon double bond in the product is. So our carbon-carbon double bond is there. You can see the 2 ethyl groups that are on the Wittig reagent are over here and over here. And so where the C double bond C is where the C double bond O was in the starting material. That's by definition of the Wittig reaction. That's what a Wittig reaction does. And so that means we first have to oxidize this primary alcohol to an aldehyde. That can be done a couple of different ways. Probably the way most familiar to you is Dess-Martin periodinane in dichloromethane solvent. That will oxidize that will be the first step of the reaction. Remember to number your steps. And so the first step of the reaction will be to oxidize the primary alcohol to an aldehyde, which looks like this. The question says you don't have to show intermediate compounds. I'm just showing it here for clarity. And then in the next step, you'll simply take that Wittig reagent that you're given and that will give you the product directly. And if you want to see a visual aid for the mechanism, these electrons go between oxygen and phosphorus, and these electrons go between the two carbon atoms. If you want also a visual aid to see where those bonds go, we did it that way in class. So that's where the two bonds go. And so you get a four-membered ring. You get the oxyphosphetane. Again, the way the question's phrased, students did not have to show this, but you certainly can if you want to. So you get that oxyphosphetane, and then that four-membered ring breaks apart. Releases a lot of strain energy, makes another very favorable phosphorus-oxygen bond. And that gives us the product. So that's just a Wittig reaction. So it's done in two steps. First, you treat the primary alcohol with an oxidizing agent like desmartin periodinane. That's a milder oxidizing agent. That oxidizes the primary alcohol to an aldehyde and no further. In the second step, we treat that aldehyde with the given Wittig reagent, which is right over here. That goes through the usual two steps of the Wittig mechanism and makes the alkene. So that's how I would approach that synthesis problem. So what you need to know in order to solve synthesis problems is all your reactions. There are no reactions that you get to forget. You have to know all of the organic one reactions as well. And in fact, the first problem used one of those organic one reactions in order to, where'd it go? Oh, I guess I've erased it. That was the one, let's just do this. That was the one where we started with an alkyl chloride and got to the carboxylic acid. The first step is an SN2 reaction, which you learned about in chapter 11. So that's how I would suggest approaching questions like that. The next question you saw questions like this on exam 1, and they're certainly pretty common on any organic exam, is questions where you're given the starting material and the reagents, and you have to figure out the structure of the product. This first one, we're given a ketone, a secondary amine, and an acid catalyst that gives us the conjugate acid of the secondary amine. And in class, we said that under such conditions, you will get an enamine. And so the way to know what the product looks like is at first you replace the oxygen with a nitrogen. I expect you to know the mechanism of this reaction as well. That nitrogen will have two ethyl groups on it. and a plus charge. So that's the iminium ion that you get at first. But then remember that we need a neutral compound. And so the way you get that is by deprotonating at one of the carbons alpha to the carbon double bonded to nitrogen. And when you pull off a proton, you make a carbon-carbon double bond. And so your final product will look like this. And of course, your nitrogen goes back to being neutral. So that's the structure of the enamine that you get. You can put the double bond on either the left side or the right side. It's the same compound. That compound is symmetrical. So that's the enamine that you would get by treating cyclohexanone with diethylamine in the presence of an acid catalyst. You need to know the mechanism also. We went over that mechanism in class. The next question involves treating a nitrile with a Grignard reagent. And we covered that reaction yesterday in class. We said the way to know what the product looks like is to draw a carbonyl group, C double bond O. On one side of the carbonyl, you put whatever is attached to the nitrile. In other words, the nitrile carbon becomes the carbonyl carbon. And then on the other side of the carbonyl, you attach whatever is attached to the metal. This is ethyl magnesium chloride. So that means there's going to be an ethyl group, rather, on the other side of the carbonyl. This ethyl group comes from the Grignard reagent. We could just as easily have used an organolithium, the same result, same mechanism, same everything, only the identity of the metal changed. And then the other alkyl group attached to the carbonyl comes from the nitrile. So I would expect that you would get this ketone. The next one involves treating this ketone with hydroxylamine in the presence of an acid catalyst, which gives you some of the conjugate acid of hydroxylamine. The type of compound you get happens to be called an oxime. I don't really care if you know that. What I do expect you to know is that we're treating a ketone with a primary amine. Remember, a primary amine is defined as one with NH2 in it. NH2 and something else attached to the nitrogen, and then with an acid catalyst. And so when you treat a ketone or aldehyde with a primary amine and an acid catalyst, you get an imine. This just happens to be a specialized kind of imine called an oxime, in which rather than an alkyl group attached to nitrogen, you've got an OH group. But that OH group on nitrogen started out in the starting material. So that OH group is just along for the ride. In class, we had an alkyl group here like butyl or benzyl or something like that. But it doesn't matter what's attached to the primary amine. In the end, you wind up losing a molecule of water. You lose the two H's on the nitrogen plus the O in the C double bond O and get a molecule of water. And you get an imine. This particular kind of imine with NOH on it happens to be called an oxime. I don't really care if you know that. It's just a special imine. But this reaction we went over in class, and we went over the mechanism as well. This is formation of an imine from a ketone or aldehyde with a primary amine and an acid catalyst. And then the next one is also a nitrile reaction that we went over yesterday. We said that if you treated a nitrile with either acid or base, with either acid or base followed by acid, then you convert the nitrile into a carboxylic acid. This is a hydrolysis reaction. So you convert the nitrile carbon into a carboxylic acid carbon. And so you can see we've changed this C into a carboxylic acid C. You're not responsible for the mechanism yet. We'll get to it in chapter 21. There is a question on the chapter 20 active that actually takes you through that mechanism in the same way as before. where we had a question like this just a little while ago on these exam practice questions. You get all the structures, and you just have to supply the arrows. So it will actually take you through that mechanism, but we'll officially cover the mechanism in chapter 21. You're not responsible for the mechanism in chapter 20. And then last but not least, here we've got a compound that is both an ester and a ketone, and we're treating it with LAH. And we just said in class yesterday, LAH is a very powerful reducing agent. It reduces carboxylic acids and esters to a primary alcohol, and it also reduces ketones and aldehydes. So both of these functional groups are going to get reduced. The ester will get reduced to a primary alcohol. And the ketone will also get reduced, in this case, to a secondary alcohol. Whoops, something's wrong. That's better. The only other thing is I would expect you to recognize that we've made a compound that has a chiral carbon atom. And whenever your product contains a chiral carbon atom, you have to show stereochemistry. So you would need to show either the compound with a dotted bond to the OH group like this, or it's an enantiomer. In other words, the compound with the wedge bond to the OH group. Either of those are fine. They are equally acceptable. Neither one of those is better than the other. If you had just drawn a straight line bond to the OH group, that will lose points. When you generate a chiral compound as your product, you're responsible for showing stereochemistry. It says that up here, for full credit, you must account for any applicable relative stereochemistry. However, if the product is a racemic mixture, which it certainly would be here, draw only one enantiomer. So that's how you approach this type of question. This type of question checks to see that you know your reactions and you're able to apply the material from class to examples that are not identical to the ones in class. You need to apply the same concepts to a situation with different particulars. And that skill is absolutely critical for doctors, because when patients come into your practice, they're going to be exhibiting symptoms that are not identical to what your professors and textbooks told you. So you need to apply the material you learned in all your classes. Good, so that's basically how to handle questions like that. But those type of questions certainly are also fair game for the exam. And then I think beyond that, all we've got is mechanisms. So the first question here involves formation of an acetal. In fact, it's a cyclic acetal. You would a question like this on active. So notice what we're given in this problem. We're given a ketone or aldehyde, an alcohol, and the conjugate acid of that alcohol. If instead of this diol, we were given just an alcohol like methanol or ethanol, then we would get an acetal with two of the same alkoxy group attached. But since we have a diol, in those cases where the diol can form a 5 or 6 membered ring, you will get a cyclic acetal. So you need to know that 5 and 6 membered rings are especially easy to form. 3 and 4, not so much. 7, not so much. But for 5 and 6 membered rings, the atoms are all in just the right place to close that ring. Let me just do a thing over here. Good. So you'll apply the same mechanism that we learned in class. Let me actually show it to you. So here's imines and enamines. And here's hemiacetals and acetals. So there's the mechanism that you need to know. It's different. In the one in the class notes, you start with cyclohexanone. In the exam question, and again, you're not going to be given this exact exam question, but in this particular exam question, you started with this ketone, which is different from cyclohexanone. And in the class notes, we used methanol, whereas here we're using a diol. However, the mechanism is absolutely identical. We start with protonating that carbonyl oxygen. And in order to do so, we use the conjugate acid of the alcohol that we're given. So here we used the conjugate acid of methanol because we were given methanol in the example in the class notes. In the exam question, we're not given methanol. We're given this diol instead. So we use the conjugate acid of that. We add an H to one of the O's and put a plus charge in that oxygen. In other words, this species here, this species that I just drew, is the same thing as this species that we're given. And so we use that to put the proton in the oxygen, not H3O plus. If you used an H3O plus ion, that would lose points. The reason is there is no H3O plus. You have to use what you're given. And so we use the conjugate acid of the alcohol in order to put that plus charge onto the oxygen. And so we wind up with this protonated species. And then the next step shows nucleophilic attack of the alcohol onto that carbonyl carbon atom. So that's exactly what we'll do. Your arrow should start at one of the lone pairs on oxygen and end at the carbonyl carbon. And then we break the carbon-oxygen pi bond and move the electrons onto oxygen. Actually, I'm just going to make my life a little bit easier. And use IPR to abbreviate the isopropyl groups. You may do the same thing as well. You do not have to do that. That is optional. But IPR is an acceptable abbreviation for the isopropyl group. If you're not confident as to what an isopropyl group is, then it's going to be hard for you to use that abbreviation. But using it is optional. And so we now have OH attached. Let me make that red so as to color code this. So we have an oxygen here. I have too many carbons. And so this whole part of the molecule came from the propane diol. And so you get this intermediate. And then if you look at what happens next in this mechanism, you see that first we deprotonate the oxygen that came from the alcohol in order to go to an intermediate that's neutral. That's the hemiacetal. And then we protonate the OH oxygen so that we're able subsequently to lose a molecule of water. And that's exactly what we'll do here. So in order to deprotonate it, we'll use again a molecule of the alcohol that we're given. You always want to use what you're given. So the alcohol uses a lone pair on oxygen, picks off a proton from that oxygen with a plus charge, and we move the electrons back onto oxygen and get rid of the plus charge. Good, that gives us this intermediate. And then we need to use our Bronsted-Lowry acid in order to put a proton onto the other oxygen. And in class, we also discussed why you have to use two separate steps to do this. You can't just use this OH and pull the proton off the other O. That would be wrong. That would lose points. The way you know it's wrong is because this would be a four-member transition state. And the way you know that it's a four-member transition state is by counting from one atom to the other one. You count from the atom that you start with to the atom that you end with. We're looking at trying to put this H onto this O. And so we'll count from the O to the H. 1, 2, 3, 4. It's a four-member transition state. And four-member transition states practically never happen. The one reaction we ever learned where you do get a four-member transition state is the Wittig reaction. And that one's special because it involves making oxygen-phosphorus bonds, which are very, very strong and very thermodynamically favored. So that's why you can get a four-member transition state in those cases, but not here. There's nothing special with oxygen-phosphorus bonds going on. So we need to do that in two separate steps. First, we pull the proton off the O with the plus charge, and then we put a new proton on the other O. And so now we have this intermediate, which is looking just like this intermediate. On this intermediate in the class notes, we lost a molecule of water by forming a new carbon-oxygen pi bond. And we'll do the very same thing over here. This oxygen will move the electrons in and form a new carbon-oxygen pi bond. And then we lose a molecule of water. That gets us to an intermediate that looks very much like the intermediate that we had before after protonating that carbonyl. So you get this intermediate. It's at this point on the reaction we covered in class that the material suffers another nucleophilic attack from a separate molecule of the alcohol. Here, instead of using a second molecule of the alcohol, there's another OH group in the same molecule. And so one thing you need to know is that especially when it comes to forming a 5 or 6 membered ring, intramolecular reactions are always favored over intermolecular reactions. Always. There are no exceptions, especially when you're forming a 5 or 6 membered ring. And here you're forming a 6 membered ring. So this OH will attack that carbonyl carbon, will break the carbon-oxygen pi bond, and move the electrons onto the oxygen with a plus charge. And the way you know that it's a 6-membered ring is once again by counting from one atom to the other. So we're trying to connect this C to this O. And you'll see if we count that far, we'll get to 6. 1, 2, 3, 4, 5, 6. So we're forming a 6-membered ring. 6-membered rings and 5-membered rings are especially stable. You learned that in Organic 1, Chapter 3. Because they're especially free of ring and torsional strain. Actually, I might as well just start over. So you get this intermediate after closing that 6-membered ring. That bond over there, which I'll color in red, is the new bond that we just formed. And now all we need to do is pull this proton off that oxygen, and then we're done. So in order to do that, we'll use, again, a molecule of the free alcohol. Here in the class notes, we used a methanol molecule because that's what we were given. Here we'll use 1,3-propane diol molecule because that's what we're given. So we just start the electron at one of the lone pairs on one of the two OH groups. Doesn't matter which one. The two OH groups are the same. We break the oxygen-hydrogen bond. And we're done. And we get the product. But the mechanism is exactly what we covered in class. All that's changed is the particulars. But the concepts are exactly the same. All we've done is changed around the structures. Good, so much for that one. These are some lengthy mechanisms, and I'm aware of that. Draw again. So this is the mechanism we're doing next. This is an imine formation reaction. The way we know that is we're given a ketone or an aldehyde with a primary amine and an acid catalyst that gives us the conjugate acid of that primary amine. Other than that, the mechanism is going to be identical to what we learned in the class notes for forming any imine. This is the example we did in class. We used acetophenone and butylamine. In this case, we have a different ketone, and I guess pentylamine instead of butylamine. But the mechanism is identical. The mechanism starts just as generally happens when you've got a reaction of a carbonyl group in acidic solution with protonation of that carbonyl oxygen. In class, we used the conjugate acid of butylamine, which we were given. Here on this question, we need to use this conjugate acid. So we need to show one of the nitrogen-hydrogen bonds in our conjugate acid. We start the arrow, we start the electron flow at one of the lone pairs on oxygen, and we break one of the nitrogen-hydrogen bonds and push the electrons back onto nitrogen. So we get this intermediate. That intermediate looks exactly like this intermediate. It's a protonated carbonyl. It's at this point that we have nucleophilic attack of the primary amine. The exact same thing is going to happen here. It's just a different primary amine. Whoops. Need a lone pair on that nitrogen. That nucleophile attacks the carbonyl carbon. We break the carbon-oxygen pi bond. But other than that, I want you to notice so far the order of the steps is the same in both these reactions. You had protonation of the carbonyl oxygen, followed by nucleophilic attack of whatever is the most nucleophilic species. We need 5 carbons on this alkyl group. Like that, 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Looks good. And then that alkyl, that nitrogen still has a plus charge on it. It's at this point in the mechanism, after the protonation and the nucleophilic attack, that we've got some proton transfers. And the strategy behind the proton transfers is to show first loss of a proton from the positively charged intermediate to make it neutral again, and then protonation of the OH oxygen so we can lose a molecule of water. That's the reason those two steps happen. And the reason they happen in the order that they do is because we don't want to protonate the OH first. That would give us an intermediate with a +2 charge, and that doesn't make much sense. Much better to lose the charge and go from +1 to 0, and then protonate that oxygen and go back to +1. So we'll do the very same thing here. First thing we'll do is pull off the proton from that nitrogen. And we'll use the base that we're given, which is, again, the primary amine. 1, 2, 3, 4, 5. So we start the electron flow at the nitrogen. We point the arrow towards the proton. Then we break the nitrogen-hydrogen bond and put the electrons back onto nitrogen. That gives us this intermediate. And then we need to put a proton onto that oxygen. We'll use again the conjugate acid of the amine. Let me see if I can do a thing here. Object. There we go. So we start the electrons at the lone pair on oxygen. We pick up the proton attached to nitrogen, break the NH bond, and put the electrons back onto nitrogen. That protonates the oxygen. And gives us this intermediate. And then we're ready to lose a molecule of water, just like we're doing over here. The nitrogen helps out by using its lone pair to form a pi bond. And then we lose the molecule of water. It's always favorable to lose a small molecule like that. That's favorable by entropy, because you're doubling now the number of particles that are bouncing around. You've got more disorder by losing that molecule of water. And so we now have one, two, three, four, five. This nitrogen is protonated. And so you get this intermediate. And now all we need to do, just like happened over here, to get rid of the plus charge on nitrogen, we just need to deprotonate it. We will use a molecule of the amine that we're given in order to do that. If we were making an enamine instead of an imine, this wouldn't be available to us. If we were making an enamine, we'd find that the nitrogen doesn't have a proton attached. So in those cases, rather than deprotonating the nitrogen directly, which is impossible, you have to deprotonate at one of the alpha carbons. And that mechanism is also in the class notes. It's right here. But as it is, since we're making an imine, all we need to do is pull that proton off, and we are done. And it doesn't matter which direction the pentyl group points. Here it's pointing to the left, here it's pointing to the right, doesn't matter. You'll get both. It's fine. So that's the mechanism of imine formation. And we just applied exactly what's in the class notes. I don't think we're done with mechanisms yet. Nope, we've got a couple more. let's look at this first reaction and describe the changes that have taken place. The C double bond O stays the same. C double bond C becomes C single bond C, and we formed a new CN bond at that beta carbon. And that N must come from benzylamine. We know that because the N is attached to CH2-phenyl, this N is attached to CH2-phenyl. So this nitrogen must have attacked in the beta carbon. In other words, this is a conjugate addition, which was another reaction we talked about in chapter 19. And here's an example of a conjugate addition here. This one actually still uses a primary amine, but there are other nucleophiles that undergo conjugate additions to alpha-beta unsaturated ketones that you will also need to know about and recognize when you see them. They are listed here in the class notes over here in section 19.13. And you need also to recognize an alpha-beta unsaturated ketone or aldehyde. You'll have a carbon-carbon double bond conjugated to the carbon-oxygen double bond, just like you have here. This is also an alpha-beta unsaturated aldehyde. You have a carbon-carbon double bond conjugated to the carbon-oxygen double bond. So in those cases, when you treat with a softer nucleophile, such as water, alcohols, primary and secondary amines, cyanide ion, there are a few others. Rather than getting addition to the carbonyl carbon, you get addition to the beta carbon. And so that's what we'll get. That's what we will expect over here. First step is going again to be protonation of that carbonyl oxygen. The way we know that is because we're in acidic solution, and the way we know that is because we're given a cation that is not a metal cation. That tells us that we're in acidic solution. That was the case for the previous two mechanisms we looked at also. In both of them, we were given a cation that's not a metal cation. That's how you know you're under acidic conditions. And so we will use this Bronsted-Lowry acid in order to put the proton onto that oxygen atom. So there's our conjugate acid of benzylamine. This is the same thing as PHCH2NH3+. I've just drawn it a little bit differently so that it's convenient for me to show the mechanism. So the oxygen reaches out and grabs a proton off of the conjugate acid of the amine. We break the nitrogen-hydrogen bond. And we get the conjugate acid of the carbonyl compound, this species over here. But now, since we have a softer nucleophile, we've got a primary amine here as our nucleophile. Amines are in the list that's in the class notes of those nucleophiles that when you treat them with an alpha-beta unsaturated ketone or aldehyde, they add to the beta carbon rather than to the carbon-oxygen double bond carbon. And that's because you get a more stable product that way than if it attacked the carbonyl carbon directly. So that's exactly what we'll show. We'll start our electron flow at the electron pair on nitrogen that will attack the beta carbon. Those electrons shift in between the two carbon atoms, just like over here. And then we break the carbon-oxygen pi bond and put the electrons on oxygen. to get rid of the plus charge. That gives us this enol intermediate. So we get this intermediate over here. The next thing that jumps right out at us is that plus charge on nitrogen. We want to get rid of that. And so that's why in the next step, we have deprotonation of that nitrogen using the amine that we're given as the base. And we will use the amine that we're given, which is benzylamine, right over here. That's going to be our Bronsted-Lowry base. That will pull the proton off the nitrogen. Then we break the nitrogen-hydrogen bond, push the electrons back on the nitrogen, and get rid of the plus charge on nitrogen. That gives us this intermediate over here. And now this type of species that we get is known as an enol. We will learn more about enols in chapter 22. What we'll learn is that in almost all cases, enols are pretty unstable, and they tend to isomerize by a process known as tautomerization to the so-called keto form, that instead of a carbon-carbon double bond, has a more stable carbon-oxygen double bond. And the way that's done is in two steps. In the first step, we use a lone pair on oxygen to reform that carbon-oxygen pi bond. We break the carbon-carbon pi bond and form a new carbon-hydrogen bond. And so we deprotonate that conjugate acid. That gives us, in fact, almost the exact same structure as our product, except there's a proton on the oxygen. That structure corresponds to this one, where you've got an extra proton in the oxygen and a plus charge. So all we need to do to get our final product is get rid of that plus charge by deprotonating that oxygen, and then we're done. We return the electrons to oxygen. And that gives us our final neutral product. Both lone pairs on oxygen, one lone pair on nitrogen. So that's a conjugate addition. We covered that in section 19.13. And we gave an example of that type of reaction in the class notes. This is essentially the same thing. All we've done is changed the electrophile from cyclohexenone to this aldehyde, this alpha beta unsaturated aldehyde. And instead of methylamine and methylammonium, we use benzylamine and benzylammonium. But the mechanism is identical. same arrows pointing to the same places. And so just let me make sure I'm not leading you astray. Yep, everything looks good. And we saved the easiest one for last. Over here, we're just converting cycloheptanone to its hydrate under alkaline conditions. The way I know it's alkaline conditions is because I'm given an anion, OH-, that is the conjugate base of a weak acid. OH- is the conjugate base of water. Water is a weak acid. So that tells me that we're under alkaline conditions. And under alkaline conditions, this hydration process, which in class we pointed out, is not synthetically useful at all. In fact, it's quite the opposite of synthetically useful. But it's something that happens readily in both acidic and alkaline medium, and is the reason why we keep small and medium-sized aldehydes and ketones of this type over a drying agent. We want to avoid this hydration happening. We want to keep that reactive carbonyl group. So normally we take steps to prevent this from happening. But in alkaline medium, of course, we don't protonate that carbonyl oxygen first. We just immediately start with the nucleophilic attack of the nucleophile onto the carbonyl carbon. And that gives us the tetrahedral intermediate, the alkoxide ion. Which looks like this. And then all we have to do is put a proton on that O- and we're done. So we just need to find something amongst what we're given that can put the proton on. The only thing we're given that can do it is water. Water is the most acidic species present in aqueous alkaline solution. So that is what we'll use. So our electron flow, again, starts at one of the lone pairs in the oxygen with a minus charge, picks up one of the protons from water, breaking the oxygen-hydrogen bond. The electrons go onto oxygen, which makes an OH- ion, and that gets you straight to the product. So that's just 2 steps under alkaline conditions. I believe I said this in class, but one of the things I've noticed in general about reactions in acidic conditions versus alkaline conditions, everything in alkaline conditions seems much more straightforward to me. There's fewer steps involved, fewer proton transfers. In acidic medium, we have more steps. There's more proton transfers. And that's it. That was the last problem on the exam. So that's pretty much it. I'll end this review session there. We've gone through all of the practice questions. Any one of these questions could have been on your exam, except of course, none of these exact questions will be on the exam. So memorizing these questions is not the way to study for this. If you want to know how to study for the exam and what you should do in order to learn the mechanisms and reactions at an appropriate level, I recommend, let me shut down ChemDraw. I recommend this document, which I've put up on Canvas, called Learning and Knowing Organic Reactions. It starts out with a list of what it means to know a reaction so that you know what to aim for. You all know that you have to know reactions for the exams. But if you don't know what it means to know a reaction, you don't know what to aim for. So this is a list of what it means to know a reaction. I don't promise it's exhaustive, but it probably gets almost everything. And after that is an application of that takes you step by step through a method that you can use to learn any reaction. In the example here, we're using Friedel-Crafts alkylation because that was a chapter 16 reaction, so that was a reaction on the first exam. But you will want to change this for a reaction in the second exam. So you might want to change this instead of Friedel-Crafts alkylation to acetal formation. So you start out by looking at the example from class. Look at an example that you know is correct. You can get it from the class notes, you can get it from the solved exam practice questions, but look at an example that you know is correct and copy it exactly. Make sure that you start and end all of the arrows at the right place. And each arrow you draw, you should know why you're drawing it. What's the driving force for that reaction? Generally, it's going to be getting rid of a charge if you can, or a nucleophile attacking an electrophile. Those are the most common ones. And then it takes you through the process of making changes to the starting material so that you get to the point of making up your own questions. And that's what you need. That's what you need to do in your studying. The way you know that you really know a reaction is if you're able to make up your own example and solve it. So this takes you through that step by step by making small changes to the examples you're given. And then those changes becoming gradually larger and larger as you learn to apply the material to other examples. So that's about it. I want to end this so that the video is available sometime this afternoon, and people can start watching it whenever they want. Other than that, that's about it. I wish you all a pleasant long weekend. I plan to spend some time enjoying myself as well, and I will see you all on Wednesday. Take care. Oh, there's a question in chat. Oh, thank you so much. Yep, you too. Have a good break. How do I do this?